Alright everybody, hello. So we're trying out this video thing and I wanted to do an example for you of an average rate of change example for a rational function. We did one in class and it was for a very simple case, so I wanted to do a little bit more involved. So I started here with a bit of a review of average rate of change. So you see here the average rate of change of a function f of x on the interval a to b is this, right? And then I just wanted to remind you here with a picture. So I drew a function, right? So here's the graph of our function. And then I picked an interval starting at this point A, ending at this point B. And of course for both A and B, I put little dotted lines, right, indicating for us that the x-coordinate is A, the y-coordinate is f of A. The x-coordinate is B, the y-coordinate is f of B. And then in red here, we have our net change, right, which is simply the difference between where we ended up and where we started, f of b minus f of a. Notice that here it is positive. And then the green dotted line, which you can see here, that is the line whose slope gives us the average rate of change, right? So I have that written here. It's f of b minus f of a over b minus a, and this is for any interval ab. You might remember we've talked about the arbitrary interval, right? So that's an interval where we don't specify a set starting point, we just call it a, and we don't specify a set ending point, we just call it a plus h. So h here is the length of the interval. Moving on to the next page, I wanted to talk to you all about this rational function, right? So here is our rational function, f of x is equal to 3 over 2x minus 5, and we're going to work on finding the average rate of change on the arbitrary interval a to a plus h. So of course, the formula for that, not surprisingly, is f of a plus h minus f of a over a plus h minus a. And that's f of a plus h minus f of a over h, because in the denominator, the a's cancel. So now let's work out what this looks like for this function, right? So I'm just going to zoom in here so that we can look at my writing really clearly. And like we've said before, it's good to start by kind of writing out what your f of a plus h and your f of a are going to be. So f of a plus h, you're putting a plus h in place of everywhere that you had x, right? Because a plus h is acting as your input. And for f of a, same thing, but instead of a plus h, it's a. So we have, I'm going to distribute here. So we have 2a plus 2h minus 5, and, well, actually, we don't even need to rewrite that, right? That's just 3 over 2a minus 5. Putting that together, okay, so we'll have 3 over 2a plus 2h minus 5 minus 3 over 2a minus 5 all over h. So you'll see that what I'm doing here is I'm just putting f of a plus h minus f of a on top and h on the bottom. So in other words, I am using this formula and putting this function into it. All right, moving on. So you can see here that this is what we call a complex fraction. In fact, let's write that here on top. This is a complex rational expression, which means that there are kind of fractions within fractions, right? And the way that we deal with this, kind of the way that we address this problem, is by removing the denominator from the top. So we are going to multiply the numerator of this expression by something that will reduce with both of the denominators, which is just the product of 2a plus 2h minus 5 and 2a minus 5. And of course, you can't just do that. You also have to multiply the denominator by that so that in the end, you will have multiplied by 1. Okay? All right, so from here, we're going to distribute. And when we distribute, distributing never sleeps. It's always the same idea. So we're going to multiply across the top So the first term, the 2a plus 2h minus 5 cancels, the 2a minus 5 stays. So we have 3 times 2a minus 5. The second term, the 2a minus 5's reduce, so we're left with 2a plus 2h minus 5 times 3. And then, of course, nothing reduces in the denominator. Okay, like that. All right. So from here, let's distribute this all out. So we have 6a minus 15 minus, so be careful with signs, 6a minus 6h plus 15 on top over h times 2a plus 2h minus 5 times 2a minus 5. And so I'm going to do this quickly just to save a little bit of time, but you see how we have like terms. We have the 6a's, so those reduce off, and we have the 15's, right? So those reduce off, and then what we're left with is negative 6h over h times 2a plus 2h minus 5 times 2a minus 5. And what I hope you all remember from before is that at this moment we can see, oh, we have an h up here and an h up down here, and those reduce too. So the final simplified version of this is negative 6 over 2a plus 2h minus 5 times 2a minus 5. Okay? So now that we have this, right, this expresses the average rate of change of this function on any interval starting at a and ending at a plus h. So over here, kind of to the left, where I have a little bit of blank space, we're going to do an example or two. But before we do that, I just want to sort of draw your attention to the fact that, as with any function, this function has a domain, right? So let's talk about the domain of this function. Looking at the graph, you all can see that there's an asymptote, and the asymptote takes place when x is 5 halves. I have it written up there. So the domain is all reals except 5 halves. This is significant because when we go to do a couple of examples, I'm going to be very careful to make sure that the interval is entirely in the domain. That means that, and I'm going to write that here, an interval is entirely within the domain if it does not contain 5 halves. Okay? If it does not include, let's put it that way, 5 halves. Okay? So again, so we're kind of keeping this in mind, and we're going to go down here. So I'm going to try very hard to kind of keep this work that we did here in line so we can see it. So let's use our work. Use the work to the right to find the average rate of change of f of x. And then let's just pick an interval. On the interval from, let's say, 4 to 10. Okay? Notice that this interval does not contain 5 halves. It starts after 5 halves. So for this interval, and I encourage you to be thinking of this as I'm writing it, a is 4, and you might think about, okay, what's h? Well, this interval is 6 units long. It starts at 4, it ends at 10, so h is 6. So our average rate of change is negative 6 over 2a, which is 8, plus 2h, which is 12, minus 5, times 2a minus 5, which is 8 minus 5, So we have negative 6 over 8 plus 12 minus 5 is 15 times 3. So what I hope you all can see is that the negative 6 and the 3 will reduce off. So we're left with negative 2/15, right? So notice that this is negative. Since this is negative, f of x is decreasing on the interval from 4 to 10. Okay, so before I finish this example, I just want to turn your attention briefly to the graph. And I want you to notice that it actually turns out that it doesn't matter what interval we pick. So you see here, I'm starting a little bit to the right of negative 2 and then ending a little bit to the right of 2, right? This is not the same interval as we did here from 4 to 10. If we look at the average rate of change on this interval, that's negative also. You can see that the average rate of change is the slope of that line. The line's tending downward. By that same token, if I pick something just here, right, and then I went over here, so I'm picking just a bunch of random intervals, oh, that's a negative average rate of change too. So we're going to kind of end this video with a right? This function is decreasing on any interval in its domain. Okay. So such a function is called a monotonic function. That's not really a word I need you to know, but it's kind of a handy word to know of, so I wanted to make sure to mention it. All right, thank you so much for your attention, and I will be making more videos like this soon. Bye.